let me first show you an example of what I'm talking about with static equilibrium. So to start out with, I made a little tower out of my daughter's blocks here. This is just going to serve as the fulcrum for my little experiment here, just kind of a stationary fixed point. So first of all, let me give you a really simple example. I'm going to use this wooden spoon here as my kind of platform. So first, let's say that I just put this spoon arbitrarily on here. As we learned in a previous problem that we did, if I just put it on here any old place, it's going to fall off because there's going to be a gravitational torque acting on the object pushing down here. And so that's going to cause a torque about this axis, and the thing will begin to rotate. So if I let it go, it will rotate. The simplest way I can get static equilibrium with this system is if I put it in such a way that the object's center of mass is directly above the support. So in this case, let me diagram it. So here's our first example of something which is at static equilibrium, right? The wooden spoon here is my system. The system is not rotating and it's not moving. Everything is totally stationary. Everything is totally at static equilibrium. Okay, so why? We know that the sum of the forces must equal 0 and the sum of the torques must equal 0. So how is that being achieved? All right, well, to figure that out, we need diagrams. We need free body diagrams, right? So let me switch to my whiteboard here. So what's going on? All right, so first of all, I have my little fulcrum, which is just a narrow support here. And then I've got my wooden spoon on top of it. And I have my wooden spoon balanced like this. And this thing is at static equilibrium. So what's going on here is, let's see where is the object's center of mass, okay? So this is the point where the object is above the support. And you'll notice that's basically the same experiment I suggested for figuring out where an object's center of mass is located. So the reason why this works at static equilibrium is because the gravitational force on the object acts at its center of mass. So as a result, if I free body diagram the spoon here, the gravitational force is going to be acting down like this, and the support, the normal force basically from the tower that the object is sitting on, is acting up like that. So these are the only two forces acting on the object. Again, the meaning of them, this one down here, this is mg. This one up here, this is basically a normal force from the tower pushing upward on the object. And static equilibrium is then going to tell me, number one, F equals ma equals 0. Which tells me in this case, the normal force minus mg equals 0. So the normal force is equal to mg. That's part of the reason why it's at static equilibrium, because the force exerted by the tower to hold up the spoon is equal to the weight of the spoon. Makes sense. Number two, we also have the sum of the torques on the object, which is normally equal to I alpha, is equal to 0 because alpha equals 0. So the sum of the torques equal to 0. Now, in order to sum torques, I need an axis of rotation. The most tempting way to do this problem, and it's a perfectly fine way to do the problem, is to put the axis of rotation at the fulcrum, where you would normally expect the object to be rotating. And in this case, you end up with the torques being exerted by both of these objects is independently 0. So the torque exerted by gravity equals 0 because L equals 0. And also the torque exerted by the normal force equals 0 because L equals 0 for that guy as well. And so you end up getting 0 plus 0 equals 0. which is of course true. But one thing which might not be so obvious, when it comes to static equilibrium problems, there's a new thing you have to be aware of, which is, since the object is not actually rotating, there isn't actually one unique choice of axis of rotation that like makes perfect sense and you have to use, because if the object isn't rotating, you might argue, well, why do I have to put the axis of rotation there? Why don't I put the axis of rotation somewhere else? Because if it's not rotating, how do you even know where to put the axis of rotation? And that's perfectly true. If the object isn't rotating, there is no preferred axis of rotation. The system actually has to be in equilibrium about every axis of rotation. So if you pick a different axis of rotation, like let's say another student is analyzing this problem and they pick their axis of rotation to be the end of the spoon. So basically what you're envisioning there conceptually is, why isn't the spoon rotating like this? Why doesn't it suddenly lift up like that? Which might be a silly question, but it's also a valid question, because in order for the object to be in static equilibrium, there has to be a reason why it doesn't suddenly start spontaneously rotating about the end of the spoon. But you can probably see how this shakes out. There is some distance here between the axis of rotation, the blue axis of rotation, and where the forces are acting. And since they're acting at the same location, this person would say, okay, I have to have the sum of the torques equal to 0, and my torques are going to be, the torque exerted by gravity is negative mgd, the force times the distance, everything's tangential here, and the torque exerted by the normal force is plus Fn times d, so we end up getting Fnd minus mgd equals 0. You can cancel out the d there, and you end up getting Fn equals mg, which is the same thing I got up here. So it works. It works. It's in static equilibrium about the end of the spoon as long as the normal force equals to mg, which it is. So it works out perfectly fine. So this is kind of like a really simple conceptual example of this. In the next video, I'll give you a little bit more of a meaty example where we actually have to do some problem solving and maybe the solution is not so conceptual.